So far, we have considered static or quasi-static situations in which the dynamics of the flow does not play the major role. Here, in contrast, we're interested in phenomena in which the combined actions of the surface tension and viscosity are the key factors. Let us begin with a simple experiment. Here, we are transferring a viscous liquid, a silicone oil held in a small tube, into another tube with a smaller inner diameter. At first, the silicone oil, 100 times more viscous than water, is deposited in the thicker tube on the left. Then we bring a thinner glass tube in contact with the air-oil interface by moving it sideways to the left. We see that the oil penetrates into the thinner tube, and we can watch its progression from the position of the meniscus, which appears as a small black band inside the tube. As the oil moves into the thinner tube, we can notice that the speed of the meniscus decreases. We can make these observations more quantitative. By performing an image analysis of the video, we can record the position of the meniscus as a function of time, and this is shown on this graph as a red curve. Clearly, the dependence is nonlinear, and the slope of the curve, which gives the meniscus speed, decreases with time. Now, let us watch a close-up of the experiment to see how the liquid begins to penetrate into the thinner tube. As before, the silicone oil has been deposited into the larger tube on the left. The inner diameter of this tube is not small compared to the capillary length. This is why the meniscus is not spherical, but deformed by the gravity. The smaller tube on the right is moved sideways and brought in contact with the oil-air interface. Then we can see the index of oil penetrating into the smaller tube, and we note that the radius of curvature of the advancing meniscus is comparable to the inner diameter of the tube. Now we have to go to the board and do some drawings and calculations to fully understand this experiment. In this experiment, we have two tubes, a large one and short, with a radius R1, and a long and thin tube with a smaller radius R2. The liquid is held into the two tubes by capillarity, with menisci having a radius of curvature equal to the radius of the tubes. As a consequence, the pressure inside the large tube, P1, is equal to the atmospheric pressure that we have outside, minus the capillary pressure, which is equal to 2 times the surface tension gamma, divided by R1. On this side, we have a pressure P2 equal to the atmospheric pressure PA minus 2 gamma divided by R2. This is our equation 1, and this is our equation 2. R2 is smaller than R1, and as a consequence, the pressure P2 is smaller than the pressure P1. This difference of pressure is the reason why the liquid is pumped into the thinner tube, because of the difference in capillary pressure between the two tubes. Now, the liquid moves with the characteristic velocity u, and we have to compute this characteristic velocity. In order to do so, we need to compute the Reynolds number to know if the flow is dominated by viscosity or by inertia. The Reynolds number is the product of density, viscosity, the radius R2, divided by the viscosity of the liquid, eta. In this experiment, U is typically 1 millimeter per second. The viscosity is 0.1 Pascal second. And the density is typically 10 to the 3 kilograms per meter cube. And the radius of the smaller tube is typically 1 millimeter. As a consequence, the Reynolds number is typically 0.01, which is much smaller than 1. And because this is much smaller than 1, the flow is dominated by viscosity. So we have a viscous flow. And for a viscous flow, the dynamics of the flow is such that viscous terms are balanced by pressure gradient. So if we write these terms in order of magnitude, the viscous term is the viscosity eta multiplied by the velocity u, divided by the square of the radius here, R2 squared, which balances the pressure gradient. That is the difference of pressure between this point and this point, divided by the length L on which this pressure gradient operates, delta P over L. Now from this, we can write the velocity u, which is also the derivative of length L as a function of time. This velocity u is typically delta P divided by L multiplied by R squared 2, this is 2, divided by the viscosity. So this is our equation 3. Now, since we have the pressure P2 and the pressure P1, we can compute the difference in pressure, delta P. So delta P is simply 2 gamma divided by R2 minus 2 gamma divided by R1. We've seen that this tube is actually much smaller in radius than this one. So as a consequence, this term is smaller than this one. So we can ignore this term in the derivation. And this is our equation 4. Now if we combine this equation and this equation, we arrive at an equation for the length L, which is simply L multiplied by dl over dt, proportional to twice the ratio between gamma and eta, multiplied by the radius R2. So we get a differential equation for L that we can integrate easily. From this, we get that the square of L is proportional to 4 times gamma divided by eta multiplied by R2 and multiplied by t. Then I take the square root of this, and I get the variation of L as a function of time as twice the square root of gamma R2 divided by eta multiplied by the square root of time. And so I get the result that I've seen in the experiment is that the index of liquid proceeds more and more slowly as time proceeds, because if I take the derivative of this with respect to time, I get u, which is going to be proportional to the square root of the inverse of time. So as time proceeds, the velocity decreases. And also I recover the experimental result that the length of tube that is invaded by the liquid grows as a square root of time, as we have seen in the data. So by comparing viscous dissipation and capillary pressure, we can understand in detail the imbibition of this tube by a viscous liquid. We will now use the derivation that we've done for the previous experiments to introduce a very important quantity, which is the capillary number. If you remember well, in this experiment, we arrived at the following result, that the velocity of the liquid within the tube is proportional to the square root of surface tension divided by viscosity multiplied by the radius R2 of the tube and multiplied by the inverse square root of time. Now you can notice that in this expression we have the ratio between the surface tension and the viscosity. It turns out that this ratio has a dimension of a velocity. And we will call this velocity u star. This is a ratio of gamma divided by eta. And this is a characteristic for a given liquid. Now, using this expression, I can rewrite the velocity u as the square root of u star multiplied by R2 and divided by time. And I can write a dimensionless value, which is u divided by u star. So I have u divided by u star, which is proportional to the square root of R2 divided by time, multiplied by the inverse of u star. Now, this dimensionless ratio has a name. It is called the capillary number. And we call it Ca. So this is u divided by u star. And this is also the viscosity multiplied by u and divided by the surface tension. This ratio evaluates the importance of viscosity with respect to surface tension. And we will use it in the following to explain the following experiment in this part of the course. Now, a final remark on the value of u star. If we consider water, for example, water has a viscosity which is 1 millipascal second, and a surface tension which is roughly 70 millinewtons per meter. And as a consequence, for water, this characteristic velocity, u star, is 70 meters per second, a very large value indeed, which shows that for water, unless we go very quickly, viscous effect will in general be negligible compared to surface tension. For the oil that we used in the experiment, the viscosity is larger. It's about 100 millipascal seconds. The surface tension is slightly smaller, typically 20 millinewtons per meter. And as a consequence, the velocity u star is on the order of 20 centimeters per second only. It is important for each liquid to have an order of magnitude of this characteristic velocity u star to be able to compare the viscous effect and the surface tension effects. In this imbibition experiment, we have seen that the balance between the capillary pressure and the viscous dissipation sets the velocity at which the liquids invades the tube. This velocity is determined by the characteristic speed u star, which is the ratio of surface tension and dynamic viscosity, and by the cross-section of the tube. We have also introduced a new dimensionless number, the capillary number, Ca, measuring the relative influence of viscous stresses and capillary pressure. We will use again the capillary number to interpret other experiments in this part of the course. But for the moment, we shall see how imbibition proceeds in a more complex geometry, namely that of a porous medium. Here, we dip a piece of blotting paper, which is 2 centimeters wide, into a bath of silicone oil, 10 times more viscous than water. We can see the liquid rising into the paper as a clear band. The liquid rises more and more slowly as time proceeds, so that we have to accelerate the movie to visualize the progression of the liquid front. We have seen two imbibition experiments, one in a small capillary tube and the other one in a blotting paper. we'll see that these experiments are very similar, but the second one has some slight differences that we'll explore now. So in this experiment, we have a piece of blotting paper, which is held vertically and which dips into a bath of liquid. So we have the surface of the liquid here, and it rises in the porous medium to a height that we will call L. If we were able to zoom onto the interface here, we would see something like this. We would see the pores of the material, which are going to be of size RP on the order of 1 micron. And inside these pores, we would see the interface of between the liquid and the air, making so small menisci with a radius comparable to RP. From the law on capillary rise, we can compute the equilibrium height of rise, which is HE, and this is proportional to the square of the capillary length LC divided by the pore radius RP. Knowing that LC is typically 1 millimeter, then that RP is 1 micron, HE is going to be typically 1 meter. In the experiment, L is typically a few centimeters, so we have L much smaller than the equilibrium height, and as a consequence, the hydrostatic pressure, rho GL, is much smaller than the capillary pressure, which is gamma divided by RP. So this means that in this experiment, we can completely ignore gravity for the dynamics of the rise into the paper. As a result, the physics is very similar to the imbibition of the tube. The only difference is that the liquid does not move into a tube, but it moves into a porous medium. And in a porous medium, the flow is governed by a law which is known as Darcy's law, which tells us that the average velocity is proportional to the pressure gradient, delta P divided by L, but multiplied by a ratio which is the permeability of the medium, K, divided by the viscosity, eta. So K is a characteristic of the porous medium. It's called the permeability. And it has the dimension of a square of a length. So K is basically an average over the square of the pore radii. So using these ingredients, we can derive the law of rise for the liquid, and we get exactly the same result as for the imbibition of the tube. The only difference is instead of having the radius for the tube, we have a geometrical factor, which is the square root of the permeability. But otherwise, we get exactly the same physics.
Capillary rise between two plates forming a wedge is especially spectacular since the distance between the plates vanishes at the corner, making the rise at the place extremely high. By using transparent glass, we can follow the profile of the rising meniscus within the wedge, which is found to be hyperbolic, as first described by the mathematician Brooke Taylor in 1712. This curve naturally stems from the law of capillary rise, since the confinement increases linearly with the distance to the apex of the wedge. The dynamics of the rise is not trivial, mainly because of the region where the driving force is larger is also the region where the friction is stronger. If we model this geometry as coexisting vertical tubes of varying radii, similar to organ pipes, we can show that the highest point of the meniscus increases at time to the power 1/3 instead of the power 1/2 for the Washburn law. Capillary imbibition is driven by the negative Laplace pressure due to the curvature of the liquid meniscus. Inside a deformable channel, the softness of the walls can be exploited to amplify imbibition. Here, a mineral oil rises between a glass plate at the rear and parallel to your screen and a thin, flexible plastic sheet whose left and right sides are kept at a millimetric distance from the glass. As this device contacts a bath of oil, we observe the formation and rise of a liquid tongue permitted by the bending of the plastic which makes the central region more confined than the edges. The imbibition process generates two wedges, one on each side of the center line. Capillary rise can thus proceed to extremely large heights with a dynamic similar to the one found in a rigid corner, namely with the distance increasing as the 1/3 power of time.